me save that so I don't forget. And then we are looking at our BST one here, right? How do I get to rename it with this? Yeah. All right, so homework for today was our what tree traversal stuff. Visit in. Okay. Well, did I just have you do in order?
Yeah, I just did that.
Okay. Well, we talked about all three already, right? Oh, I actually didn't give you examples for the other ones. We talked about them. The high level, this is what they are, but and we probably have enough information how to do them, but we'll look at the three of them today, and then we'll look at we're going to talk about tree balancing, but not actually implement that. I kind of made a suggestion last class that ADL trees are a little bit rough. It's good enough to talk about them in here. And then we're going to talk about the heap data structure, which is an implementation of a binary search tree. Okay, so tree traversal, we're going to talk about in order, and this has to do with how do we visit nodes in order to get the value out of it. So if we visit the nodes in the right order, we should get, if we're following in order, we should get an output that is a sorted output. That's how we know we've done it right and how we know that our tree was built right. It's almost like a litmus test. Okay, how did it go? Shouldn't have been too horrible. Way better than the last assignment, at least. All right. So, although I will say that a high percentage of you did get the last assignment done one way or another. you kind of got something out, but which was impressive because it was more difficult than I had intended. Okay, so as a reminder, when we visit in order, we're visiting the left child first, then ourselves, then the right child. So if we're looking at a tree like this, if we're visiting this tree in order, we're going to visit this guy, which means this guy will visit this guy first, then himself, then this guy, then this guy, this guy, then this guy. We'll try to go here. We didn't. This guy, then this guy. All right, so that's the order, and it ultimately visits, does them in order. All right, so we're going to go ahead and add an ability to our binary search tree. We already have a display. I'm just going to create a void display in order function. All right, which is kind of dictating that we're going to do this in a certain order. And we'll go implement this guy. I'll put it down near our display here. And we can do that same checking, you know, if it's not equal, then I'll do something, otherwise do something else if we want. So we can really steal most of this code, but we won't just call the roots display. So what we're going to do is we're going to teach we're going to teach our nodes, BST nodes, how to visit themselves in order. Okay. So display in order for a BST node, we need to go write that guy. But that's effectively what a binary search tree's display in order will do. He'll say, hey, if I have stuff in this tree, ask the root to display himself in order. Otherwise, spit out empty tree. Person probably shouldn't have called this function, yada, yada, yada. All right, so we're going to teach our binary search tree nodes how to display themselves in order. Okay. Go to our implementation of this. All right. Now, look at what we're doing right now. Right now, we are displaying the payload for our normal display. We're displaying the payload. Then we're asking our left child to display themselves. Then we're asking our right child to display themselves. So ourself first, then left child, then right child. Ourselves first, then left child, then right child. We were already written pre-order. Our normal display visits our tree in pre-order right now. We display ourselves. We ask our left child to display themselves. We ask our right child to display themselves. Okay. So we've actually already written this guy, unbeknownst to us. So display in order. Actually, I'm going to steal this guy. I'll just move our payload into the middle of the sandwich, just like that. Left child first, then ourselves, but only after this guy has finished. Because the left child is going to try to visit their left child, who's going to try to visit their left child, and so on and so on and so on. So there might be a whole bunch of stuff that happens in that single call. Because this is kind of a pseudo recursive call, but we do need to make sure that we're calling our display in order function here, not the normal display. Similarly, display in order. So display in order visits the left child in order, then visits ourselves, then visits the right child in order. Make some sense? So if we call display in order on this, we should get all of our numbers in order, sorted order. And that will be our litmus test. Project can't be saved. Seems amazing. All right. So let's see if we can run it. So we'll call display in order here. Two, 2, 3, 3, 6, 6, 7, 8. So it's giving us our data in the correct order. Make sense? All right, so that should have been the homework. Not too bad. Okay. And then we could see that, well, we already saw pre-order. So our display function, just display here. This shows our data in pre-order. And if we look at this data, that data isn't overly meaningful to us if we visit it in pre-order. All right, that might be a order in which we traverse the tree relative to another algorithm. We're just kind of showing that, hey, we can traverse this binary search tree in all sorts of ways. The fact that we are doing it as a binary search tree and storing the data in some kind of ordered way probably indicates that the best way to traverse it's going to be in order so that we actually can pull our data out of it in a sorted fashion. And that's going to make some sense to us when we talk about heaps. Okay. Similarly, if we go ahead and we implement post order. So actually what I'm going to go ahead and do is in our binary search tree, I'm going to update display to be called pre-order. And make sure our nodes know the same thing. This is display pre-order. Display pre-order. Display pre-order. We didn't change the logic at all. We just made sure that our old display method, which happened to actually traverse pre-order, is now called pre-order. Let's see if we can save now. Big money. It's very interesting, seeing as though I'm able to run the program, which presumably is requiring an internet connection, but it won't let me save the program. Can I try to share it? That work? No, not at all. Cool. All right, so now we're going to go ahead and we're going to write display post order, which you can imagine is not going to be earth shattering, right? So we'll just steal this function. Display post order. Make sure we call, common mistake when you're copying and pasting these is you forget to update which version of the functions that you're calling. Display post order should call the node's post order inside. Otherwise you get very weird results and you wonder why, and you chase around for 20 minutes until you finally realize that you were still calling the function from the guy you copied from. Don't ask how I know that. Speculation. All right, so we'll teach our nodes also how to display post order. Steal this dude. It's called post order. Make sure you're calling the right functions here. Post order for both of those. And then make sure you actually update the logic to call them in post order. Post order says visit left, then right, then ourselves. So that's logic for post order. Okay. Again, nothing earth shattering. Go to main. Now we'll say display post order. We already had display pre-order, except we used to have it called display post order. Let's see what this guy looks like. There's our data in post order. We look at that. The data doesn't at a glance seem all that meaningful. It is useful in certain applications, certain algorithms that deals with breadth first versus depth first searches, where you're going all the way down into your tree looking for a value versus looking for a value at various levels within your tree. So I'm telling you, there are potentially applications for visiting nodes in your tree in these various ways. But very clearly, since binary search trees follow this BST rule set, everything to the left is less than or equal to, everything to the right is greater than. That in order thing really seems to shine as being this guy is storing our data in a very specific way that allows us to pull it out in a sorted manner. Okay. So questions about any of that? Not too bad. I could see with this assignment, some of you maybe went down some weird pathways that made it a lot more difficult than it needed to be, but and that has more to do with recursion is tough, right? Thinking recursively. So even though I usually would refer to something like this as pseudo recursion, so we're currently inside of a function called display preorder, and we're calling display preorder in there, even though it's another instance of our node's preorder. It's a different node who we're calling preorder on, but it's still a recursively feeling thing. Recursion is still going to be a rough thing. If you talk to some of your fellow students who are currently in the 470 class with me, the language theory class, where we have to do everything recursively, they will be able to give you the feedback. Maybe you could ask them about at the get together today, that they actually understand recursion way better now. You go into that class terrified about recursion, then you hate Scheme, the programming language we're using, and then you sort of kind of start liking Scheme, and then all of a sudden you understand recursion accidentally, and then you have trouble going back to iterative thinking. because you are so used to doing things recursively for an entire semester. It's kind of a fun thing, but I promise you eventually recursion won't be so bad. You know, recursion is when a function calls itself from within itself, and that is just a kind of put your brain in a little weird knot, something like that. So, but hopefully when you saw us write this pre-order, do this first, then do this, then do this. Recursive solutions almost always look simple on paper, you know, but then when you try to chase it, it becomes kind of intimidating. All right, so let me try to save one more time or roll the dice. Bad news bears. Wonder why that is. I would say I could try to change Wi-Fi, but I don't know what kicked the Zoom people off. So I'll just make sure I try to save later. Otherwise, we'll lose everything. But this wasn't that big of a change. Okay. I did mention, and we won't go that far down the. Well, actually, I can prove it here in a second. I mentioned that the order in which we add values to our tree does matter, right? In terms of the actual structure of our tree. For instance, if I add 3 to this guy first, he will be the root node. What if I had added 8 first? 8 would be the root node to our tree, right? So we would have an entirely different tree if I only made that one change. I came in here. And I'll switch this back to our in order. And all I did is I took that line and I put it before the 3. So at the very least, we have forced 8 to be the root node of our tree. But we'll see that visiting in order still gives us our data in order. 2, 2, 3, 3, 6, 6, 7, 8. So we know the data is still being stored in some sort of ordered way because it's following those BST rules, even though we didn't have to go very far to immediately make the exact same data stored differently, because we're convinced that 8 is now the root node and 3 will be to the left of 8, since that's the guy we did second, right? So actually, what will our new tree look like? This is actually a good example. That's our new tree. 8 is our root node, and everything is to its left. This is an unbalanced tree, right? Driving down the road, you see one of those trees that the highway people have. You see one of those trees that the highway people have cut out to like get off the telephone lines. So the tree is all right half. There's nothing on the left. That's what we're dealing with here. Now we say, okay, fine. It's just a funky looking tree, not the end of the world. Well, what if we're using that tree to do searching? Because it seems like this idea of storing stuff in a certain order might lend itself to problems that involve order being important, which sometimes is a thing that exists in our world, right? We have this world of fairness and that kind of stuff. So we could imagine if, and this is actually somewhat of a, let's say that we were looking for the number 3 in here. Good example for this. We're looking to see, is 3 in this data set? My old version of the tree, we would have found 3 right away, right there at the root, done. Right? Depending on especially if we searched it using pre-order, right? If we searched it pre-order, we would check the node we're currently looking at right away. Ah, root node 3, done. Super fast, right? Okay. If we used post order, we'd eventually get to a 3. We'd actually find this version of 3 down here. And actually with 3 at the root, and we were doing post order, 3 is the dude we'd find last. So that's kind of the least efficient way of finding that 3, right? If we didn't have 3 farther down the tree. In order gives us kind of maybe on average, a fairly consistent time to find a value because of the order in which we're visiting it. provided that our tree is roughly balanced on both sides. If the tree is not balanced, then we have a very lopsided tree like this. We might go down many layers until we finally get to our answer, rather than kind of hover at the top. Because if we have a balanced tree, presumably we have this idea called self-balancing trees, where after we add something to the tree, so for instance, in this case, we added the 8 initially. That's the root node. The tree's balanced. There's only one node in it. He's not lopsided. Then we add the 3. Okay, the 3 is the 8's left child. We're still balanced. I mean, balance roughly says that one side isn't more than one deeper than the other side. You know, you're not necessarily going to be able to find perfection, but as long as one side isn't any deeper than the next side. Well, now we add, let's say we add the 2. So now all of a sudden you have the left side being 3, 2, and the right side being nothing. In that particular case, let me, I'm just going to steal that slide for this example. In that particular case, let's say my tree currently looks like this. I'm going to add this 2. Well, let's go this route. I add the 8. Is the tree unbalanced? No, it's fine. There's only one element in it. It's not lopsided. I add the 3. I say, is the tree unbalanced? We're going to say it's a little bit left heavy, but it's fine, right? It's barely, you know, the left side has a depth of 1. The right side has there isn't 1. We're okay. But then all of a sudden we add the 2. And now we're like, okay, this tree's starting to lean a little bit. And from a, now in real life, we might say, okay, it's not that bad. You know, we're not getting power tools yet to start trimming this thing, but yeah, it's starting to kind of lean a little bit. But if we're thinking about an algorithm and data efficiency, and really a lot of times when we talk about in the 490 class, you're going to do quite a bit of talking about what's called the big O notation, the efficiency of different searching algorithms and sorting algorithms, and some of them are n squared or n log n and things like that. What they're really talking about is the average time the algorithm will take for different values. Sometimes you get lucky, you roll the dice and it runs even faster just because of the nature of how your data was organized. But really what you want to do is you want to say, how well will this perform on average? Is this something that I can rely on to give me good performance? Okay, as opposed to something that can either be great performance or horrific performance, right? You know, which was like our example before. It's either the first value we found or the last value we found. And we probably don't want it to be that lopsided if we can help it. We'd rather have something that's almost consistently decent than something that is sometimes great, but let's say often horrible or something along those lines. So in this case, we ask the question, is this tree lopsided? Is it unbalanced? Yeah, it is. The left side has a depth of 2, let's say in this case, could have a depth of 3, depending on how you count it. Usually I will look at it as 0 indexed. So this is level 0, this is level 1, this is level 2. So this guy has a depth of 2, this guy has a depth of 0. Unbalanced, because the difference between those is greater than 1. Okay, so we might say, how do we fix this tree? And this is where we come down to this AVL tree idea, where we'll look at the rules of AVL, probably next time, just at the high level. We won't implement it, not because it's horrific to implement, it's just overly complicated and we don't need to spend time writing it. It's one of those things you fight through, come out with some scars, and you just move on with life. But you know, we'll say that we'll cover it theoretically. But the general gist of any self-balancing tree algorithm, and there's many, there's probably, I don't know, 10, 12 balancing tree algorithms. Famous ones are AVL trees, red-black trees, splay trees, a couple different algorithms for how do you self-balance a tree. Realistically speaking, if we're just thinking about this generically as humans, effectively what we're going to do is like a chiropractic adjustment, right? This guy's a little bit off, so we're going to kind of twist them. You twist them, get a little pop, right? And so in this particular case, what we need to do is with the AVL tree version of this is we're going to give them a little bit of a twist to the right. So effectively that 3 becomes the new root node. We're still following the BST rules, and now we have a balanced tree. Move on with life. Now, we'll say that that balancing act, in that case, that was a simple balancing act. Sometimes we got to do 2 pops, right? You got to twist this way and then twist another way, and in order to get it right, that's where things start getting messy. You know, it's just like going to a chiropractor. It's like, it hurts here. Why'd you pop over here? That's how they make the big bucks. So in any case, that's kind of how these self-balancing algorithms work, is by making adjustments like that. Okay. Ultimately, with the goal of keeping your tree as level as we possibly can so that its performance for doing operations on it is consistent. Okay. That's the big idea. Now, where does stuff like this come into the greatest play? The 430 database class is probably going to talk about things under the hood, how databases are put together. Databases often use binary search trees as part of the data structures for building them. So you imagine if we use databases to do searches for things, SQL, our query language for relational databases, you know, is going to probably rely on some level of performance. So we probably want our more modern databases to have our data stored in some sort of interesting way that searching it becomes a little bit of a faster thing, other than our much older databases like flat file databases, which were just stored in text files and not necessarily organized in an overly complex way, which then didn't lend itself to performance. Easier to implement the database, slower in terms of the actual performance, right? But now we sort of have a weird world we live in where our processors have gotten so fast. So only in really large data sets does the human being actually notice that performance difference, right? There's many circumstances in computing today. In fact, we probably could say most circumstances in computing today, if we do something in the most efficient way and we do something in the least efficient way, the human being won't be able to tell the difference in terms of the speed in which it runs. You know, yeah, you can in Unix, there's a little time function you can run from the command line where you say, I want to time how long this program takes to run. And, you know, you would get 2 different numbers back from that. You know, and a lot of times time is based on time on the CPU. But both of them are going to be way less than a second, right? It's going to be some fraction of a fraction of a fraction of a second, but this one was 9 times higher. But none of us can really tell the difference between 0.2 nanoseconds and 0.8 nanoseconds. Make sense? Computers are fast, all right? So a lot of these things are things that are important to the computer scientists because we need to be able to leverage them when it counts. But a lot of times it isn't necessarily important to us. So one of the things that we want to go through when we're solving problems in industry is, do I do this in the most optimal way? Or, because sometimes the most optimal way is not the easiest to understand way. Even if you personally understand it, you might not necessarily be the one who's going to be managing this or maintaining this software 2 years from now. So you might decide, you know what? Our computers are fast enough to solve this problem. I'm going to write this in a much more straightforward fashion that's going to be easy to maintain and give up a little bit of efficiency rather than write this in the most efficient way possible, regardless of understandability, because it's reliant on speed. We make those same decisions when you're a video game writer today. Games need to be fast, right? So maybe if you're working on the code for your start menu options, you're probably not in your video games measuring frames per second on your start menu. Not a whole lot of stuff is going on, right? Once you get into the game and you got explosions and things like that going down, you want that to be as efficient as possible, and you don't care how hard it is for next month's programmer. Make some sense? Okay, so these are some of the decisions, some of the things that should go through our head as computer scientists when we're running the problems, when we're solving problems rather. Okay, so how do we, one thing we will do in here is detect depth. So if I go back in here, in this, and we'll just use this guy as an example, I want a individual node, because remember, a tree is a tree of trees. I want an individual node to be able to report to me what his depth is. Okay. So, where we say, how deep do we go? So if I ask, what's the depth of this tree? This is 0, this is 1, this is 2, this is 3. So the lowest node here is a 3 for depth. Okay. Let's see, what tree did I have before? I had this guy, right? This is 0, this is 1, this is 2, this is a 3. So the depth of this tree is a 3, even though a majority of the tree sits at level 2. So we would say, is this tree off balance? It's not. The right side has a depth of 3. The left side has a depth of 2. It's in one of each other. We're fine. We don't need to rebalance it. Okay, even though we're not actually going to write the rebalancing aspect of it. But how do I ask this tree, what is your depth? That's the question that we need to solve. How do I ask the tree that I'm looking at right here what his depth is? So what is the depth of this tree? How did you calculate the depth of this tree? As a human being, we just looked at it and say, well, this one's a little bit longer, so we'll just count down this dude, and there's our answer. It's a 3. Okay, but if we're a computer, this is our entire world when we're at the BST, our instance of a binary search tree, right? We have a root node, and I'm asking that root node, yo, buddy, what's your depth? And he's going to spit back out, it's a 3, but how did he calculate? How did he calculate that? Go ahead. The longest. So he said, well, let me check with both of my kids, right? He's going to say, hey, left son. What? That's the lesser son. All right, so left son. What is your tree's depth? Because it's a tree of trees. Right son. What is your tree's depth? And then the parent will make the decision. He'll say, which of you two reported back to me with the deeper depth? Does that make sense? And that's how he'll report his answer. Okay, so this guy will have a depth. So well, let's just look at from this guy's perspective. This guy's going to say, okay, well, what's his depth? Well, he's going to say, well, you know what? I don't know. My whole kingdom is right here in front of me. My 2 lieutenants, my 2 kids, they can report back the information about their world. So this parent's going to say, well, my depth is 1 plus, because I'm part of the depth, right? Okay, so it's 1 plus the, and that probably doesn't matter whether you count yourself or not, as long as you're consistent. But we're going to say it's 1 plus the maximum depth of our left and our maximum depth of our right. Okay, so he's going to ask his left child, hey, what's your depth? And then the left child's going to say, well, it's the maximum depth of it's 1 plus the maximum depth of my left child, and or the maximum depth, the maximum depth of my left child or my right child. And he's going to look around, find out that the world's pretty lonely. So he's going to yell back, 1 pops. My depth is 1. Okay, so he's pretty lonely here. So he's going to report back to dad, it's 1. Now, he also asked about the right child. Right child said, okay, well, I do have 1 heir to the throne. So he's going to ask his left child and not get there isn't one. So he's going to say, well, my depth is whatever my right child says his depth is. Right child's pretty lonely. He's going to say, Dad, my depth is 1. This guy say, okay, well, my depth is 2. 1 plus the depth of the child. So this is 1 plus 0. This is 1 plus 1. Dad, my depth is 2. Dad, my depth is 1. So this guy's going to say, my depth was the maximum value of my depth of my left child and my depth of my right child. So my maximum depth was 2. 2 plus 1 is 3. So this guy says, okay, I'm dealing with a maximum depth on this side is a 2 from my child. My maximum depth on this side is going to be a, let's see, a 1 plus 1 plus 1. That's actually a 3, right? It's a 3 over here. Because this is a 1, he reported to Dad, so Dad is 1 plus 1, which is 2. Reported to Dad, 1 plus 1 plus 1 is 3. So he said, hey, my depth is 3. Over here, he's going to say, my depth is 1. He said, well, he's going to have to break the tie between his two kids' kingdoms, right? Left child says my depth is 1. Right child says my depth is 1. The maximum of 1 is, and 1 and 1 is 1. So he'll report back up that my depth is myself 1 plus the maximum of 1 and 1, which is 1. My depth is 2. So the ultimate root node is going to say my depth is the maximum of 2 or 3. And the maximum of 2 or 3 is 3. So he's going to report that his depth is a 3. Make some sense? Okay, so our homework, let's write it, I'll put it after this homework assignment. This is what we just covered. What's the height of a tree? Homework is give our binary search tree the ability to report its depth. It's a link to the code and the self eval. All right, let's see if I can save yet. Otherwise, I'll keep trying throughout the day. Oh, saved, good. Get this as our starting point. All right, any questions what I'm asking you to accomplish? All right, we'll end a little bit early. Don't forget we have the CS get together down the hall, so go run to the restroom, whatever, so you can be down there on time, because there's usually like a little game or whatever at the beginning to get to know your classmates, and that game is the thing you want to take seriously, because the people who do well in that game are the ones who get the best prizes. I'm not kidding. I'm not just selling it on it. Like in the past, I don't know what they ordered this year, but the $150 prizes are the ones that go to the winners of that. And then the $6 prizes are substantially farther down the line. So I encourage you to be in there by noon and ready to strongly participate. Plus, it's a good opportunity to get to know your fellow computer science students and upperclassmen and the people you can help and that kind of stuff. Questions, comments, concerns, bribes? All right, and let's see. I'll put up our exam just real quick. Give me about, well, I mean, it's just go through the slides so you can ask any questions if you want online. So the midterm is actually going to be, quote, in class next Tuesday. So that's your allotted time to do our midterm exam before the fall break, because fall break starts next Thursday. So any classes after 4 p.m. next Wednesday don't meet. So fall break will be, you'll be on fall break a week from today, right? What day is today? It's Wednesday. We're good. Okay. So next Wednesday, I thought today was Tuesday. Next Wednesday in class is the actual class time you will have allotted to you for taking the midterm. On Monday, I'll go through the slides and tell you the things that I think are important for the midterm, but I'll actually probably put the midterm up Monday morning sometime. So you just need to get that into me sometime by midnight on Wednesday. So you can decide what time, when you want to take it, because I know that some students, none of you, I'm sure, but do leave for break a little bit early. So, but officially your allotted time to take the midterm will be during our class time a week from today, next Wednesday. Go ahead. I'll design it to, I mean, since it's supposed to go in a 50-minute period, I'll design it to take maybe 30 minutes, but I'll probably put the time limit on it to, I don't know, 2 or 3 hours. Like, it's not a time, I don't mean for it to be a time tested thing. So I would say you should leave yourself about an hour to take it. But if you think you're an extra slow test taker, you want to take your time on it, give yourself a couple hour block, because you will have to do it all in a single sitting on Blackboard. But I'm not going to put you might make me put a time limit, but I won't put like a aggressive time limit on it. Maybe it's only 3 or 4 hours or something, whatever I can set it at, but something like that. All right. And you can ask more questions on Monday or online or whatever, but it's closed book, closed note. You can use your calculator if you need it. There'll be at least one conversion question on there, like there is in all my exams. So convert from binary to hex or something like that. Otherwise, it'll be mostly programming stuff that we've covered this semester, or talking about things, the algorithms we've dealt with this semester. All right. All right, so I'll see most of you here in a few minutes down the hall. It's in S118. Or 118B, I guess.